Image processing is everywhere, and chances are you are enjoying its applications every day. When using social media apps, reading QR codes, playing video games, using software like Photoshop, and pretty much in every feature of your smartphone camera. You are starting your journey into image processing and computer vision, or you have some experience using popular tools like OpenCV or MATLAB and you'd like to brush up on the basics, this course is for you. Although you will probably end up using professional libraries that contain efficient tools for industry applications, the objective of this course is to give you a chance to tap into the details of the algorithms behind image processing. This will give you a better understanding of what's going on inside, and you'll make much better use of professional tools in the future. Before we start, there are some things you should know. First, the objective of this course is for you to learn image processing. We will not create a computer vision library or use a professional library like OpenCV in depth. Instead, I will introduce you to the basic concepts and some of the most popular algorithms in computer vision and computational photography. Once you've acquired this knowledge, you'll make a better use of image processing tools in the future. Every code example you'll see in this course is written in Python 3 and runs inside a Jupyter notebook, so you should feel comfortable with this programming language and platform. If you are not very experienced in Python, I recommend that you consider taking an introductory course from our library, like the one titled Learning Python. If you're new to Jupyter notebooks, you will probably catch the basics in this course. But if you'd like to learn more, I recommend the course titled Introducing Jupyter. And lastly, to get your system up and running, you'll need to install the Anaconda distribution and OpenCV for Python 3. Don't worry, I'll show you how in the next videos. For this course, you'll need a Python 3 setting with NumPy, Matplotlib, Jupyter Notebooks, and OpenCV. If you already have a Python 3 setting and you know how to install all the necessary packages, please do so. If not, the easiest option I recommend is to install the Anaconda distribution, which comes with everything we'll need, except for OpenCV. Just go to anaconda.com and download the installer for your system. In this course, you'll see all examples running on Windows 10. But you shouldn't expect big differences on a Mac or Linux computer. Once you've downloaded the installer, run it and proceed with the installation wizard. The default options are OK. After installing Anaconda, it's time to install OpenCV, which is very easy. Just run the Anaconda prompt and type in the command line pip install opencv-python. That's it. Your system is ready to go. Let's test your setting to make sure you have everything you need. The first step is to open the Anaconda Navigator. To run your notebooks, you have two options. You may launch the Jupyter Notebook application, which is the regular notebook platform in your browser, or you may launch the Jupyter Lab application, which is a fancier option with many additional features like showing line numbers and tabs for opening many files in one browser window. Or you may launch the Jupyter Lab application, which is a fancier option with many additional features like showing line numbers and tabs for opening many files in one browser window. This is the one I'll use. This will open a tab in your browser where the application will run. At the left, you'll see a Folders tab where you can browse starting at your User folder. Now let me browse to my exercise files. Let me go to Notebooks, CV, and I'll browse to Chapter 1, Video 4. Once inside, I'll double-click on the notebook named testingyourenvironment.ipynb. Notice that all the files in that folder are visible, and if you double-click on komodo.jpg, it will open on a new tab. If you need more space, you can always resize the navigator or collapse it by clicking on the folder icon. Although I will show you every cell running for all exercise files, you may want to take a minute to pause the videos and read through the notebook code and comments. Take your time. Now notice that this notebook is showing its cells with results below. Those are the results from a previous run of this notebook. So every time you want to run a notebook from the first cell, I recommend that you restart the kernel and clear all outputs. You can do that from the menu, like this. Now let's run this notebook. You can do this by selecting a cell and pressing the Run button. The keyboard shortcut for this is Shift-Enter. The first cell should print your Python version. Next, we'll print your NumPy version and create a matrix just to make sure it's working. The next cell opens and displays the Komodo dragon picture with matplotlib. The last cell opens and displays the same Komodo dragon using OpenCV. As you can see, the cell shows an asterisk at the left. This means that it's not done yet, and that's because this cell opens a new window with the picture, which I must close before the cell can finish. This image looks larger because it's shown at its full resolution. Let me close this window so we can move on. And we are done. If everything went well, your setting is good to go. Now you know how to access the notebooks you'll see in the videos ahead. So please have them handy to replicate the procedures I'll show you, and watch out for the many visual artifacts these procedures will create in your images. There are a few ways you may represent images in a computer. One of the most popular is the raster image representation, which is the type of images we'll see in this course. Up ahead, we'll get to know raster images and some important details about them. First, a raster image consists of a matrix of pixels, which are the small dots or squares that compose a picture like this smiley. Images may encode color, but they may be grayscale or even black and white. There are several file formats used to store pictures. Some of these formats involve compression, but not all of them. And lastly, an image may be stored at different resolutions. Let's start tweaking some pictures. In this notebook, let me show you how you can create raster images in grayscale and color with integers and floating point numbers. Let's look at the first cell where I'll create a simple grayscale image. Notice that I'm importing NumPy and Matplotlib's pyplot module in lines 4 and 5. In line 6, the assignment of retina to figure formats is done to get the best resolution from Matplotlib's imshow, which is the image show function. You'll see this line in every notebook ahead. So next, I'm creating a 3x3 NumPy array, and I'm initializing it with numbers between 0 and 255. These numbers represent shades of gray, where 0 is black and 255 is white. Look at the comments to make sense of these shades. Lastly, in line 12, I'm displaying the image with pyplot's imshow function. This function takes an image object as an argument and optionally a color map. For grayscale, we'll use the gray color map. Let's run it. Notice that the plot shows the row and column coordinates. Since this is a 3x3 matrix, the image is extremely magnified. In the next cell, I'm printing the image with the print function to see how it looks in a text representation. I'm also printing the data type of 1 pixel. As you can see, it's a matrix of 32-bit integers. Moving on to the next cell, let me show you the same thing for a 3x3 color image. This time, Each pixel is encoded as a red-green-blue triad. That is to say that this image has 3 channels of intensity per pixel. Each number represents the intensity for its color. We'll talk about color shortly. Look at line 7 and notice that this time I turned off the displaying of X and Y axis in PyPlot. Also notice that the image show function doesn't need a color map anymore because this image has all the color information it needs. Let's run it. And once again, let's see its text representation and the type of an intensity value. As expected, this is a 3-dimensional array of 32-bit integers. Lastly, let me show you the same image, but encoded with floating point numbers between 0 and 1. This is the same image we saw before because the image show function uses the maximum value as the maximum intensity. And finally, let's look at its text representation and type. This image is made of 64-bit floating point numbers. Color may be encoded in a variety of ways like RGB, RGBA, CMYK, or HSL. In this course, we'll exclusively use the RGB encoding, where each pixel is represented as a vector with 3 channels, red, green, and blue. RGB is usually encoded as a 24-bit bitmap. RGB is usually encoded as a 24-bit bitmap, meaning that each color channel has a number between 0 and 255, where 0 means 0% intensity of its color, and 255 means 100% intensity. 24-bit color encoding is also known as true color. The first cell in this notebook is the same we saw before. I'm initializing IMG with an array of 3 by 3 pixels, and every pixel is an RGB triad. According to this encoding, take a moment to pause the video and read the comments at the right based on the combination of colors in the image. Notice that all pixels have either 0 or 255 in their intensity values, except for the bottom right pixel, which is 50% gray. This image has trivial combinations of full intensity colors. For example, blue and green yields cyan, and red and green yields yellow. Also notice that when all 3 channels have the same value, we get a shade of gray. Now let's modify one pixel. In this cell, I'll change the bottom left pixel to go from black to orange. The bottom left pixel is at row 2, column 0. That's why I'm indexing IMG with 2, 0, and the third index is for the color channel. 0 is red, 1 is green, and 2 is blue. Now I know the tone of orange I want. It has 100% red and about 80% green with no blue. So to change this black pixel to orange, I can set its red channel to 255 and its green channel to 200, as you can see in lines 3 and 4. I've left the blue channel alone since the pixel was black anyway. Now look at line 6 to see how the image show function can print partial images. Well, because Python allows us to do so. Here we'll print the sub-image at row 2, column 0. And there you have it. Finally, let me display the whole image just to make sure that we changed the bottom left pixel. And there it is. Let's move on. Opening image files and saving images into files are the start and finish of image processing respectively. Let's look at some important aspects of image file management. In the first cell, let me open a JPEG file using the pyplot imread function. JPEG is an image format that uses lossy compression. That means that the compression slightly modifies the image, but it can achieve amazing compression ratios. Look at the imread function call in line 7. The file name is stickanimals.jpg, and I've assigned the returned object to a variable named JPEG. Before moving on, notice that the files we are opening are all in the Notebooks folder. Let's see the JPEG image. As you can see in the axis, this image is a bit over 600 by 600 pixels. Now let's see another version of the same image I had previously saved as a PNG file. PNG is another image format that uses lossless compression. That means that all pixels are left unchanged, but the compression ratio isn't as good as JPEGs. This time the file name is stickanimals.rgba.png, and I'm assigning it to a variable named PNG. The two images look the same, right? Well, they're not. Let's look at their dimensions. In this cell, I'm using the numpy's shape function to get the dimensions of both images. As you can see, both are 617 by 648 pixels, but the JPEG has 3 color channels, while the PNG has 4. In the next cell, let's inspect the first pixel. That's pixel at row 0, column 0. Aha! The JPEG is encoding the pixels with integers from 0 to 255, and the PNG is encoding them as floating point numbers from 0 to 1. And there's the fourth value for the PNG picture, which is 1 for this pixel. Let's confirm this in the next cell. Let's see their data types. I'm looking at the data type of the first channel in the first pixel of each image. The JPEG uses 8-bit unsigned integers, and the PNG uses 32-bit floating point numbers. All of this is because of two reasons. First, PNG supports a fourth channel for every pixel. This extra channel, often called alpha, encodes transparency. This is the RGBA encoding. And second, the imread function encodes PNG files as floating point numbers from 0 to 1. All other formats like JPEG or BMP are encoded as integers from 0 to 255. So to be able to work with one single format for all pictures, let me show you a function I wrote to convert an RGBA with floating point numbers to RGB with 8-bit integers. As the comment in this cell reads, to do this conversion, we need to change 3 things. First, we need to get rid of the A channel. Second, we must multiply each value by 255. Third, we must round the results. Fourth, we must ensure that all values are between 0 and 255. And 5, we must convert the data type to 8-bit unsigned integers. You may want to take a moment to hit pause and read the code to convince yourself that it's indeed performing that conversion. The function definition starts at line 13. It's called adapt.png, and it performs steps 1 and 2. Then in line 16, it calls another function to perform steps 3, 4, and 5. This function definition starts at line 24. It's called adapt.image, and I wrote it because we'll need it when manipulating images where the results may go outside the 0 to 255 range. Let me just run this cell. I've made these functions available in a separate source file named eccv.py, which you may import in your code. There's a copy of it in every notebook folder. Let me show you. Here you can see these two first functions and many others we will need throughout the course. Let's go back to the notebook. Here's how I suggest opening PNG files to work with 24-bit RGB images. In line 6, I'm calling the adapt PNG function with the result of imread. Next, I'll display the picture, but notice that I'll also print the data type of the first pixel and its value, just to make sure everything went well. And there you have it. Its data type is uint8, and it has integers within the expected range. Lastly, let's save a file. This time I'm extracting the horse as a subarray named horsey. The imsave function receives the desired file name and the image variable to use. And now let's look at the folder. There it is, horsey. The resolution of an image is its level of detail, or its pixel density. We're about to see an image at several resolutions. Bigger resolution images are suitable for printing on a larger area, but they require more computational power to process. In this notebook, we'll take a quick look at the same picture at 3 different resolutions. The first cell opens the file named dog 800 by 600.jpg. Before running this cell, look at line 6. I'm importing RC params, which are the runtime configuration parameters, because I want to manipulate the size of the pictures that will be displayed by the image_show function. To do this, in line 8, I'm setting the figure size parameter to a maximum width of 10 inches and a maximum height of 8 inches. Now, here are 2 things you shouldn't worry about. First, these units may not be actual inches in your screen. On my screen, they are more like centimeters. And second, the ratio of these dimensions will not affect the ratio of your images. So your images will be limited to the width and height you specify here, but they will not be stretched out of their original ratio. Let's see the picture. That's my spoiled mixed-breed dog who sits like a pug. Remember, this image is 800 pixels wide by 600 pixels tall. This resolution is enough for us to see some detail in the grass and the flowers at the back. Now let's look at a lower resolution version of the same picture. If you look closely, you may notice a pixelation artifact in the dog's eyes and snout. That's because this picture has a resolution of 300 by 225, but it was displayed at the same dimensions in the screen as the previous one. So technically, this picture has less dots per inch, or DPI, than the previous one. This second picture is appropriate for displaying at a smaller size. Now let's see an even smaller resolution version. This one is 120 by 90 pixels, so the pixelation artifact is extreme. Once again, this picture isn't necessarily bad. It's a lightweight file, so it would be suitable as a thumbnail or preview for the high-resolution picture. Just like this. This is the same low-resolution picture displayed at a much smaller size. Imagine this as a thumbnail in a folder view among many other picture files. Rotating images at right angles and flipping them horizontally or vertically involve transposing pixels and inverting their order. NumPy supports these operations for images without changing the order of the pixel data. That's RGB. First, let's open a picture of a street in my neighborhood. There we can see the iconic water volcano in Guatemala. Now let's rotate it 90 degrees counterclockwise. This is possible with NumPy's ROT90 function, which reorders pixels while maintaining the color channels as RGB. Notice in line 3 that the function receives two arguments, the image and the number of rotations to perform. This time we want one rotation. There it is. Notice that I'm assigning these rotations to the same IMG object, so I'm updating the image. Now to rotate the image 90 degrees clockwise, we may rotate it counterclockwise 3 times, as you can see in line 3. And we are back where we started. Now let's flip the image horizontally. This is how a mirror reflection would look. We can do this with the flip left-right function, as you can see in line 4. This function inverts the order of pixels in the horizontal axis. There it is, a mirrored image. And lastly, let's flip the image vertically, which is not the same as putting it upside down by rotating it 180 degrees. This vertical flip is performed with the flip up-down function. Let's see it. You could easily write functions for these operations as an exercise if you'd like. It's time for your first challenge. As you may have guessed, for all challenges you'll have to write code on a Jupyter notebook. Please read every cell and follow the instructions in the comments. For this challenge, you will manipulate some pictures. These pictures are taken from 3 files in the first cell, and you'll work with the images in variables traffic, penguins, and ice pops. You don't have to modify this cell, you can simply run it. Your first task is to find the RGBA image. One of these images is a JPEG file, and the other 2 are PNGs. One of these PNGs is encoded as RGB, and the other as RGBA. You have to find out which one it is. Your second task is to convert all images to an 8-bit unsigned integer encoding. Feel free to use the functions I showed you. These functions are available in the ECCV source file, which is imported in the first cell. You can always open the file to see the code. Your third task is to display the 3 images in 3 separate cells. You have to show the access for some pictures and hide them for others. Just follow the instructions in the comments. Task 4 is to manipulate the images with rotations and flips. Once again, you have 3 separate cells for this. First, you have to flip the traffic picture. In the next cell, you have to rotate the penguin's picture. Lastly, I have something special for the ice pops picture. This cell will copy ice pops to IMG. Just run this cell without changing it. Now the next cell will multiply IMG by 2 and show you the resulting image. You don't have to write code in this cell either. You'll just have to run this cell 10 times and notice how the image changes each time. If you lose count or want to run the experiment again, you can rerun the previous cell to start over. After running the experiment, try to explain what happened. This should take you about 15 minutes. When you're done, check out the next video to see my solution. Here's my solution. For the first task, I simply printed out the dimensions of the pictures with the NumPy shape function starting at line 10. So here we can see that penguins is the RGBA image because it has 4 elements in the third dimension. For task number 2, I used my adapt_png function for penguins, and I used my adapt_image function for ice pops after multiplying it by 255. I could have used adapt_png for this as well. Now for traffic, I didn't do anything because it's already encoded with 8-bit unsigned integers. Then, starting at line 14, I print the dimensions and data type of all pictures. The result shows that they're all now 8-bit integers with 3 channels. Task 3 was easy. I printed traffic with axis, and then penguins and ice pops without axis. Then we have task 4, where I flip traffic horizontally with the flip LR function. Then I rotate penguins minus 90 degrees, which is the same as 3 rotations of plus 90 degrees. And lastly, let me show you what happens to the ice pops picture when I double it repeatedly. Here we go. 1, 2, 3, 4, 5, 6, 7, 8. Whoa, it went black. 9 and 10. So what do you think happened? Well, recall that all the values in these images are encoded in 8 bits. So every time we multiply this image by 2, we are losing information because the most significant bit of the multiplications is lost. Another way of looking at it is that multiplying an integer by 2 is the same as shifting its bits to the left by 1 position. In the end, we can only do this 8 times before we have filled every byte with zeros, and that's why the image eventually goes black. In many applications of computer vision, color isn't very useful, so all that data may slow down the computing process. That's why removing color is a common practice. Let's see a 2-step process of going from full color to black and white. First, we must convert a color image to grayscale. This conversion means reducing the encoding from 3 or 4 color channels to only 1 brightness channel. There are several ways to do this, not just one. We may stop at a grayscale image if that's what we want, but the second step is to convert the grayscale image to black and white. This conversion would allow us to encode each pixel with just 1 bit. Now, this is not as easy as it sounds. You'll see why in a minute. Let me show you a simple way to convert a color picture to grayscale. It consists on calculating the average of its red, green, and blue intensity components, and use this average as the only intensity for its pixels. That is, a single channel picture. First, let's open a picture of a play space. In line 11, I'm using an object named toys for the picture, and in line 13, I'm printing its dimensions. Here's the picture, and its dimensions are 629 rows by 804 columns. This is a relatively low resolution. In the next cell, I defined a function to go through all the pixels and calculate the RGB average to finally return the resulting grayscale image. You may want to pause the video and examine the code. And please keep in mind that our objective is not to create a professional library, but only to illustrate what's going on. In line 11, I'm using this function to get a new object named toys.gs for the grayscale version of toys. Let's see it working. It's taking a while. This is exactly what I expected for a grayscale version of this picture. Also notice at the beginning of the result that the image has only 2 dimensions. But it took a while. That's because I used 2 nested loops in my code, and since Python is an interpreted language, it takes its time to do the job sequentially. Luckily, Python is known for its MATLAB-like vector notation. So in this next cell, we have a one-line implementation of this average calculation. It turns out that a dot product takes care of it. Let's see how long it takes now. Well, it was faster. So now that we have a faster way of doing this, let's try it on a high-resolution picture. Let's see it first. Now this picture is over 5000 by 3000 pixels, so even the vector operation may take a while. Let's see how long it takes. There you have it, a nice grayscale image with a rather high resolution. Average grayscale doesn't always look very natural to the human eye or brain. A more natural alternative is to calculate a weighted average with different weights for red, green, and blue, based on luminance or human perception. A popular distribution of weights is 0.299 for red, 0.587 for green, and 0.114 for blue. Let's work with the play space image again. In the next cell, let me create the same average we calculated before in line 4 and a weighted average in line 5. Notice the distribution of weights. Now let's print both pictures side by side, as you can see starting at line 8. Here we have the regular average at the left and the weighted average at the right. Try to notice the difference in the shades of gray. Notice how the truck and the mat at the back look different. Now let's see it again in the fruit picture. Here's the color version. And here we have the grayscale versions. One difference I can notice are the leaves, which look much lighter in the weighted grayscale image. Now let's talk about converting grayscale images to black and white. This is often useful in computer vision, where you may need to identify objects, and black and white is all you need. Let's work with the play space image again. In this first cell, let me open the file, convert the image to a weighted grayscale, and display it. Now let me show you a function I wrote in the ECCV file to turn each pixel to total black or total white based on a threshold. This is the grayscale to BW function starting at line 30. It receives a grayscale image and a threshold to compare every pixel. This function traverses the whole grayscale picture one pixel at a time, changing them to 0 or 255, depending on whether they are greater than the threshold or not. Notice that the returned image is also grayscale with integers from 0 to 255. Let's go back to the notebook. In this cell, I'm calling the grayscale to BW function with a threshold of 127, the middle shade of gray. This certainly looks like a black and white picture that came from the original picture, but there seems to be a lot of missing detail. To have a better understanding of what the 127 threshold we used means in this picture, let me show you a histogram of the pixels in the grayscale image. A histogram is a plot of the frequencies of values in the data points, that is, the pixels. So this plot is showing how many pixels have the same value. In the horizontal axis, we have all values from 0 to 255, And in the vertical axis, we have how many pixels have each value. Yes, this image has a lot of pixels. Over 500,000 actually. Remember, 0 is the black end and 255 is the white end. Each bump means that our image has a significant amount of that shade of gray. So just looking at the histogram, we may get an idea of which threshold levels to try. For example, the lowest point dividing the dominating bumps seems to be near 115. So let's try putting the threshold there and see how it compares to the 127 threshold image. And that's what we have in the next cell. The threshold for the picture at the left is 127 and 115 for the one on the right. Take a moment to notice the differences. I noticed some improvement in the outlines of the truck. Let me tell you about a nice technique called adaptive thresholding. As you may know, an image may contain segments with different lightings and shades, so a static threshold for turning it into black and white may favor some segments and ignore others. For these images, different thresholds apply to different segments. Here we have a tutorial about image thresholding at the OpenCV website. It shows two functions to perform adaptive thresholding on a Sudoku image with a big shadow over it. This shadow is irregular, so the picture is ideal for this example. As you can see, we have the original image, then its black and white version with a global threshold of 127, which is very much ruined by the shadow, and then the two adaptive threshold results. One is the adaptive mean thresholding, and the other is the adaptive Gaussian thresholding. Both are doing a great job at extracting the numbers and the lines. I decided to replicate this code with a different Sudoku image. Let's see it in a notebook. First, let me show you my Sudoku image. Notice that this one doesn't have a big shadow like the picture in the OpenCV tutorial, but it does have different backgrounds in the 9 number blocks. It seems like this would get in the way of a global threshold. Now let's look at the histogram for this picture to get a sense of its global threshold. A threshold of 127 doesn't seem so promising, but we'll try it anyway. So in the next cell, we have a modified version of the OpenCV code. By all means, take a moment to read it, but here are the highlights. In line 6, I'm setting the global threshold to 127. You can try other thresholds later, especially the ones in the comment. In line 7, I'm reading the image with OpenCV's imread function. Next, I'm applying a blur filter to it. We'll talk about filters a bit later, but this is performed to get rid of tiny changes by smoothing the picture, especially if it has a big resolution. In line 9, we have the OpenCV function to produce the black and white image with a fixed threshold. The result goes to the th1 object. Then, in line 10, we have OpenCV's adaptive threshold function to get the black and white image with adaptive mean thresholding, as one of the arguments specifies. For each pixel, this function sets the threshold at the average of a specified neighborhood area for that pixel. This area is a square with the pixel of interest at the middle, so this block size must be an odd number. That's the next to last argument with the value 33. In line 11, we have the same function performing adaptive Gaussian thresholding. This is similar to the previous one, but it performs a weighted average of the pixels in the neighborhood area. Their weights are bigger near the pixel of interest and smaller the farther we go, in the shape of the Gaussian bell curve. So let's see the results. Here we have the original image and the result of a global threshold of 127. As you can see, some numbers are missing parts and the lines are gone. Now here we have the results for adaptive mean and Gaussian thresholding. Both are pretty good. And don't worry about those tiny leftover spots. We'll see some methods to get rid of them later. Now let's go back to the histogram. In an effort to get a better global threshold, you may want to rerun the next cell with different thresholds. Two I found interesting are 215 and 225. So go ahead and try those thresholds. Lastly, let me show you what happens when you apply adaptive thresholding to photographs. Let's see it for the play space image. As you can see, the borders are highlighted, making it look artistically drawn by hand. Go ahead and try it with your own pictures. It's time for another challenge. Let's remove color from an image. Once again, please follow the instructions in the comments. Your first task is to print a color image of your own. For that, you must copy the file into this folder. Task number 2 is to convert that image to grayscale and display it. Task number 3 is to plot a histogram of your grayscale image for you to try and pick a suitable global threshold later. Lastly, for task number 4, create 2 global threshold images and compare them. For this, you may use functions from OpenCV or the grayscale to BW function in ECCV. This should take you about 15 minutes. When you're done, check out the next video to see my solution. How did you do? Here's my solution. First, I used a picture I took of a sunset at the beach. There it is. That's the Pacific Ocean, by the way. Next, I converted it to grayscale using the weighted average method I showed you earlier. Now here's my histogram. Looking at it, I picked 2 crevices I found interesting for the thresholds. These are at 115 and 175. So in the next cell, I applied these thresholds in lines 8 and 9. It took a while because I used my grayscale to BW function. Here are the resulting black and white pictures. One of the main problems with global thresholding is that each of these images has captured some important details that the other missed. And sadly, they both missed the sun. Let me tell you about convolution filters, a special category of operations that can be applied to grayscale and color images. A convolution filter consists in taking a kernel, which is a small square matrix of odd dimensions, and we calculate the value of a corresponding pixel in a new resulting image exactly where the center of the kernel overlaps with the original picture. This new pixel is a function of the kernel and the overlapping pixels. In this example, the new pixel is calculated with a weighted sum of the overlapping values. You can think of the kernel as the set of weights you'll multiply by the values in the overlapping pixels of the original picture. The kernel is overlapped with every pixel in the original picture to produce the resulting picture. Let me show you an example. Let's suppose we have the grayscale image at the left and we want to run the 3x3 kernel at the right throughout this picture to produce a new one. If we start with this overlap, the resulting value in the new image will be the result of adding all the products of the overlapped values. That's 1 times 4, plus 2 times 0, plus 1 times 2, and so on. That comes to 56. At the neighboring pixel to the right, we get 66. At the next one, 76. And so on and so forth. Now you may be wondering what happens with the pixels at the edges. In this example, we're talking about one level of missing pixels outwards, because our kernel is 3 by 3. If our kernel was 5 by 5, then we'd be missing 2 levels of pixels outwards. So we have a problem with corner pixels and also with border pixels at the sides. Luckily, this is a solved problem. There are several methods to handle edges, and they all involve extending the picture prior to running the filter. In our case, we could make the picture grow outward by a thickness of 1 pixel, and these pixels may be black, some level of gray, or an extension of the edge pixels, like this. Notice that the extended pixels are the same as the edge pixels, and corner pixels extend diagonally. This way, we can freely run the kernel through the picture at the corners and at the sides. Lastly, let me tell you a few details about convolution filters. First, they take long to compute because we must traverse every pixel in the original picture, each time performing as many multiplications as the kernel's elements plus 1 summation. However, convolution filters are highly parallelizable because, as you may have noticed, each pixel in the resulting image is a function of the original picture and the kernel. In other words, all pixels in the new image are independent from each other. This means that computers with a graphics processor with hundreds or thousands of cores can do a great job at running convolution filters. Virtually every software tool you use for image processing or computer vision takes advantage of this fact. OpenCV is no exception. Also, convolution filters are capable of highlighting certain features of pictures, as you will see up ahead. Now, you might be wondering how this works with a color picture. Well, for color images, the process is applied to each channel, which is equivalent to having a 3D kernel with the same shape for all channels. However, you may use a 3D kernel with different contents for each channel. Let's experiment with average filters, which use the kernel to calculate the average of all overlapping pixels. This average is the new pixel, and it produces a blurring effect in the image. This time we'll use the picture of a house. Notice that this image has a relatively high resolution. Next, let's run an average filter using OpenCV's filter2D function. We'll use this function because it would take too long with a straightforward function of our own. It turns out that the mathematics behind convolutions has a lot of non-obvious shortcuts that libraries like OpenCV use to their advantage. In line 3, I'm creating the kernel with a 7 by 7 matrix where all elements are 1/49th. If you think about it, that's the weight we need for each pixel if we want to calculate an average. Notice that I'm creating a matrix of all ones, and then I'm dividing it by 49, which is 7 squared. In line 4, I'm using the filter2D function, which takes as arguments the image, then the depth, which is the encoding size of the image, like 8 bits or 32 bits. A value of -1 is used to match the original image depth. The last argument is the kernel we just created. The result goes to a variable named blurred. You might be wondering how this 2D function works with a color picture, which is 3D. Well, the 2D kernel we just created is copied to create a suitable 3D kernel for all channels in the color picture. Let's see the results. I can certainly tell that this image is blurry. Now let's compare the original image and the blurred one side by side. Notice how each part of the picture has been blurred. Now, if you'd like to compare at a better level of detail, you may display sub-images. For example, in this cell, we have a vertical section of the pictures from column 400 to 799. This way you can compare any section of the pictures. In this example, we used a 7x7 kernel. Now the size of the kernel translates to how blurry the resulting image will be. So now let's see the results for a 3x3 kernel. Notice in line 5 that now I'm dividing the all ones matrix by 9, which is 3 squared. Notice how slight the blurring effect is now. Not all filters perform the same weighted sum operation. Median filters can also blur images by picking the median value instead of the average. To showcase median filters, let's work with a grainy picture of a damaged photograph. This picture shows several spots and lines caused by damage to the physical photograph, as well as a grainy artifact. Let's use OpenCV's median blur function in line 3. As arguments, it takes the image and the size of one side of the square neighborhood where the median will be selected. I'm using a square of 5 by 5 pixels. Notice that this filter doesn't use a kernel because it works with the original pixels exclusively. Let's see it. At first glance, we can see that the damage marks are diminished. We can barely see the lines, and the spots are pretty much gone. But how does this compare to the average filter we saw before? In the next cell, I'm displaying them side by side. At the left, we'll see the average filter blur, which is created in lines 5 and 6. And at the right, we'll see the median blur. Notice that I'm using a 5 by 5 kernel because I want to make a fair comparison of these filters. Indeed, the median filter did a better job at getting rid of the lines and spots. Now let's zoom into these two images in vertical sections. Let's start with the leftmost section. Both images have leftover lines and dots. But now we have an emerging feature in the median blur picture. Notice how the horizon looks different in these pictures. That's because median filters work with the actual pixels in the original picture. That means that no new colors or shades will come up, but only copies of the original pixels. This tends to preserve and highlight edges like the horizon we see here. Now let's see a middle section. Once again, we have the damage marks less visible in the median blur image. Notice that the plantation shadows look a little sharper in the median image. Now let's see a rightmost section. Now we can see a stronger highlight of edges in the flowers and the plantation outlines. Is this a good thing? Well, it all depends on the effect you are trying to make. To me, it seems a bit unnatural. Great. Now let's see the same procedure on a different image. This time we'll work with a vintage picture of a group of workers. This picture is quite grainy and also shows some damage. Let's perform a median blur to this picture. Now, because of the level of detail in this picture, in line 3 I'm using a smaller neighborhood of 3 pixels. It definitely looks a little better. And now let's see it side by side with its average blur counterpart, created in lines 5 and 6. To be fair, This filter uses a 3x3 kernel. At first glance, the details look better to me in the median filter image, the one on the right. Let's zoom in on 3 sections again. Here's the leftmost one. I like the median filter's job at highlighting the details without making it look too blurry. The edges around the worker do look a bit highlighted, but not too much. Also, look at the detail in the shirt and buttons. Let's see the middle section. Once again, notice the detail in the tools. Now there's a strong artifact in the edges of the saw. Lastly, let's see the rightmost section. I have included a third image for you to apply these filters. This one is a grainy picture of a face. Try to experiment with several kernel sizes to see if you can improve the picture. While average filters calculate the average in the neighborhood of the pixel of interest, a Gaussian filter calculates a weighted average using a kernel with values that match the Gaussian bell curve. Here we have a 3x3 Gaussian kernel. Notice that the center is the highest weight, and the weights get lower and lower as we go farther from the center. Let's open the picture of a house we saw before. In the next cell, I'm calling OpenCV's Gaussian blur function in line 3. It takes as arguments the image, the size of the kernel, and the border type. Notice that the width and height of the kernel can be different, but they must be positive odd numbers. Let's see the blurred image with a 7x7 kernel. There you have it. It's not easy to tell the difference between an image blurred with an average filter and one blurred with a Gaussian filter. That's why in the next cell, I'll show you all 3 blur filters at once. This time I'll use a large kernel to make it easier to tell the difference between the median, average, and Gaussian filters. This will be a 15x15 kernel. Notice the extreme blurring and edge artifacts of the median filter image at the right. Now, like I said, it's tough to tell the difference between the average and the Gaussian filter results. So let's zoom in to see the main entrance. Now we can see some differences. Look at the light fixtures above the door, and also the one next to the door. The Gaussian filter seems to have preserved some of the detail in spite of the blurring effect. Now let's talk about edge detection filters, in particular Sobel filters. If you pay attention to what the convolution of a kernel is doing, you'll notice that it's assigning more or less importance to certain pixels. So you may expect to extract certain features of images depending on the patterns you use in a kernel. Here we have 2 Sobel filters. The first kernel detects vertical edges, and the second detects horizontal edges. In both kernels, notice that the center pixel has a value of 0 along with its row or column. Also notice that the kernel has opposite signs in the values at the edges. These simple kernels yield very interesting results. Let's work with a picture of penguins. To keep things simple, I'll convert this image to grayscale. Notice in line 13 that I'm using OpenCV's convert color function for this. By applying Sobel filters, we'll detect all edges in this picture. Let's start with a vertical Sobel filter created in line 3. I'm assigning the resulting image to an object named VR Edges. By VR, I mean that this is a vertical filter where the change from positive to negative goes to the right. So V stands for vertical and R stands for right. Let's see it. Notice that edges with a strong vertical component are highlighted. Also notice the lack of horizontal edges. Now let's use the opposite kernel, the one facing to the left. That's why I'm creating a new image named VL edges, as in vertical facing to the left. Let's see the two images side by side. Look closely and try to notice that both images are highlighting vertical edges, but the edges detected by one filter were not detected by the other filter. That's because one kernel highlights changes when the intensity drops, while the other highlights changes when the intensity rises. So, to get a combined image with all vertical edges, let's add the two images. In line 3, I'm using OpenCV's add function to create the VEdges object. Let's see the result. Great! Now let's do the same for horizontal edges. In line 3, we have the horizontal kernel facing down, and in line 9, we have the one facing up. Let's see it. Once again, pay attention to the different edges detected. The one at the left is highlighting the tops of the penguins' heads, and the other one is highlighting the floor. Now let's add the two images in the H-edges object. There we have all horizontal edges. So now that we have all vertical and horizontal edges, it makes sense to add them all. I'm doing that in line 3 by adding V-edges and H-edges. Let's see it. There it is, an image that highlights all edges in the penguin's picture. Just for fun, let's turn that picture into black and white and get rid of some noise. And that's what I'm doing in this cell. This black and white picture was created with a threshold of 127. Feel free to try other thresholds. Again, just for fun, let's invert that picture to make it look like a drawing. I'm using OpenCV's bitwise not function for this. There you have it, a nice drawing of some penguins. Are you ready for your next challenge? This time you'll create your own convolution filter and try it on your own pictures. Task 1 is to print a color image of your own as usual. Just make sure to assign it to the img variable. For task 2, you have to define a kernel of your own. Try to apply some logic in its values and try to predict how it will behave. Your kernel may be 3x3, 5x5, or any size as long as it's a square of odd sizes. You simply have to modify the kernel definition in line 9. Notice that this kernel leaves the picture unchanged. You don't have to modify the next cell, just run it to compare your original image with the filtered image. Task 3 is to create a second filter. Again, modify the identity kernel. Try to be creative. It may be something related to the previous kernel or something totally different. Finally, run the last cell to compare your two filtered images. This should take you about 15 minutes. When you are done, watch the next video to see my solution. How did you do? Let me show you my solution. For task 1, I used a nice picture of two Komodo dragons, one of my favorite animal species. Look at line 9. Since I decided to play around with edge detection filters, I converted the image to grayscale in this step. For task 2, I decided to create a variation of a Sobel filter. This one has a diagonal pattern like a straight line with a positive slope. Let's see it working. Notice that the positive slopes are indeed highlighted. My second filter is the negative slope version of the first one, so I'm expecting to highlight the other diagonal edges. Let's see it. Yes, the negative slopes are highlighted. Lastly, let's see both images side by side. There they are. It looks like the grass got in the way. Maybe some blurring at the beginning would have been a good idea. Image downscaling means taking an image of a certain resolution and producing a new image with a lower resolution. But why would we want to do that to a perfectly good image of a tiger? Well, maybe the high-resolution tiger is taking up too much storage space, and we only need to print a thumbnail, which will look a lot smaller on a screen. Like this. This smaller tiger is the same low-resolution tiger, not the high-resolution one, and it looks good enough for me. Another reason would be to perform operations on a picture to extract data from it, where a lower resolution would yield the same result as a higher resolution. This would help speed up these operations. So what's the problem we face when downscaling an image? Let's say we want to downscale this image by a factor of 3. That is, we want to convert a 6x6 image into a 2x2 image. The problem is to determine the color we need in each pixel of the lower resolution image. Looking at the original picture, we can see that there are 4 large squares composed of 9 pixels each, and each of these squares corresponds to 1 pixel in the new image. The problem is to decide what to do with the pixels in each square to produce the new pixel. We could use an average, a median, or even complicated functions that consider the neighboring pixels or gradients. The problem becomes more complicated when the shrink factor is not an integer, like a factor of 1.5. As you can see, the problem in these cases is that we won't always get an integer number of pixels to work with. But this problem also comes up when trying to shrink an image with a resolution that's not divisible by the shrinking factor. There are several ways to tackle this problem. Ready to downscale a picture? Let's work with a close-up of the water volcano we saw before. Notice the resolution. It's 389 rows by 536 columns. Now let's downscale it. For this, I'm calling the downscale function I wrote in ECCV. Let's see the code. My function starts at line 40 and it receives 2 parameters, the picture pic and the scaling factor n. Feel free to hit pause and examine the code. Here are the highlights. In lines 41 through 44, I'm dealing with the problem of downscaling an image with a resolution that's not divisible by the scaling factor. I'm simply disregarding the remaining pixels at the end of the rows and columns. This isn't bad at all because I'm only disregarding up to n-1 pixels per row and column, and I'm simplifying the problem greatly. In line 47, I'm creating an empty image object of the smaller dimensions. Then, inside the nested for loops, I'm calculating the average of every n by n square in the original picture for each color channel to produce each pixel in the smaller image. Alright, let's go back to the notebook. In this cell, I'm downscaling the volcano picture by a linear factor of 4. That is, I'm making the image area 16 times smaller. Also notice that I'm using the adaptImage function because the downscaler may have left some pixels outside the acceptable range for the ImageShow function. Let's see it. There's the expected pixelation. Now let's see the two images side by side as usual. Notice the resulting dimensions, grab your calculator, and try to verify that the correct downscaling was performed. The difference is visible everywhere. Look at the volcano slopes and the roof shadows. Now let's display both images at a suitable size for the lower resolution image. It's difficult to tell the difference at this size, so we might as well use the smaller image. Now let me save the smaller image in a file named smaller.bmp. Here it is. It looks okay to me. And lastly, let me repeat the process for a different picture. But now let's use a shrink factor of 10, so the resulting picture is 100 times smaller. Look at the resolutions. I discarded 3 pixels in every row and 9 pixels in every column of the original picture. Can you tell by looking at the pictures? I can't. Image upscaling is a more ambitious operation. Now we want to produce a higher resolution image from a lower resolution one. It may sound impossible at first, and I claim that it is impossible indeed. Now, the fact that something is mathematically impossible doesn't necessarily mean that there aren't pretty good approximations. Well, there are some upscaling algorithms that can stretch images well enough to fool many humans. Here's the problem we face when upscaling an image. Let's say we want to do the opposite as before. Now we want to upscale this image by a factor of 3. That is, we want to convert a 2x2 image to a 6x6 image. The problem is now to determine the colors we need in each pixel of the higher resolution image. The trivial solution would be to fill all high-resolution pixels with the same color of the low-resolution pixel they're extending. But this would look pixelated because it would be simply an enlarged copy of the original picture at a higher resolution. A better solution would try and guess what colors in the high-resolution pixels would produce the missing details. If interpolation algorithms come to mind, you're onto something. Here we can see that the high-resolution pixels at the borders are trying to create a smooth change to the color in the neighboring low-resolution pixels. And once again, a non-integer growth factor is a complication because we're left with low-resolution pixels creating non-integer numbers of high-resolution pixels. Now let's try our hand at upscaling an image. This is a bit more complicated than downscaling. This time we'll start with the downscaled image from the previous notebook. There it is. Now I'll use the upscale by 2 function from ECCV. Let's see it. The function starts at line 58 and it only receives the picture as an argument. In lines 59 through 64, I create the larger image object with an extension of its last row and column. That's because my algorithm calculates the higher resolution pixels by interpolating with the neighbors. So these extra pixels are there so that the last pixels have neighbors. Now don't let the body of the nested loops spook you. All it's doing is calculating the 4 new pixels from each lower resolution pixel. Let me show you. Let's say we want to calculate the 4 pixels that would expand the top left pixel in the leftmost picture. So let's fill up the top left square in the empty picture at the right. The easiest higher resolution pixel is the top left one because it's just a copy of the original pixel. So this pixel alone gives us this smaller pixel. Now the top right pixel is the average of the source pixel and its right neighbor. So these two produce this one. Remember, the resulting color is the average of the two neighbors involved. Moving on, the bottom left pixel is the average of the source pixel and its lower neighbor. So these two produce this one. And lastly, the bottom right pixel is the average of the source pixel and its lower right neighbor. So these two produce this one. So that's what's being calculated in the body of the nested loops. Okay, let's go back to the notebook. Now let's see the upscaled image. Now let's compare it with the original, smaller image. Notice the resolutions in the axis. The low resolution picture is at the left and the higher resolution picture is at the right. I can definitely see some improvement. Now let me upscale the enlarged image further and compare it with the small image. The higher resolution picture seems a bit blurry, but definitely less pixelated. Let's quickly save the larger image into a file. Alright, now that we have reduced an image to 1/16 its original size and then stretched it back up 16 times, let's compare the original resolution volcano picture with the final shrunk and stretched image. This is gonna be fun. Notice that the dimensions of these two pictures are the same. Now, visibly the final image lost information at some point. This happened in the downscaling process where 16 pixels were packed into one single pixel. It's time for another challenge. Let's resize some pictures. As usual, task number 1 is to pick a picture of your own and display it. Task number 2 is to downscale that image to the resolution of your choice. Feel free to use the downscale function from ECCV or any other function either made by yourself or from a library like OpenCV's Resize function. Finally, task number 3 is to upscale your image. You may do that with your original image or with the downscaled image from the previous cell. Again, feel free to use the upscale by 2 function from ECCV or any other. This should take you about 15 minutes. After you're done, watch the next video so I can show you my solution. Let me show you my solution. For this challenge, I used the picture of a pizza in a brick oven. There you have it. Now for task 2, I made a comparison of a downscale with a linear factor of 4 made by my ECCV function with one made by OpenCV's Resize function. As you can see in line 10, this function receives the target size as an argument. So I cheated by looking at the resulting size from my function and then sent those dimensions to OpenCV's Resize function. Let's see the comparison. At the left we have my downscaled image, and at the right is the one by OpenCV. At this size, I honestly can't tell the difference. For task 3, I decided to blow up the small image 4 times to get the original resolution. Once again, I compared my implementation with that of OpenCV. Let's see it. Just like before, I can't tell the difference at this size, which I guess is good news. Before wrapping up the course, let me introduce you to image cuts, an application of image processing in the amazing art of computational photography. These are the techniques used by photographic software like Photoshop or your smartphone's camera. Cuts are a family of pixel-level operations. It's just like cutting a printed photograph with scissors. Cuts are useful for stitching pictures together, as we'll see shortly. But cuts have a wide variety of other applications, like seam carving, for example, which is a technique for resizing images by adding or removing pixels with the same type of cuts you are about to see. A very natural application of cuts is in stitching two images together. Let me show you an example. Suppose that we have these two unrelated images and we want to create one novel combination of them. The picture at the left was taken by myself one day I went for a walk, and the picture at the right is a professional picture of a tiger in what appears to be a jungle. One way to stitch these two pictures together is to simply put them one next to the other, like this. But as you can see, there's a vertical artifact that gives away the fact that these are two separate pictures. Instead, we can grab the two images and cut them in a very special pattern that minimizes the perceived changes in a seam, like this. Then we can put the two pictures together right at the cut. Let's stop right before we complete the stitch so we can see where the seam is. Interestingly, it's surrounding the plant at the left. So this is how the final picture looks. Notice how peculiar this picture looks. It's difficult to find the seam even for someone with a keen eye. So how can we stitch two pictures together? First, we must define an overlap between the two pictures. This is the number of pixels we will overlap the two pictures horizontally. Next, we calculate the error between the overlapping parts. This can be as simple as the squared difference of the pixels. Then, inside the error section, we find the path with the minimum change. This is the seam. Lastly, we stitch the images at the seam. Let's see these steps in the tiger example. First, we start with the two images which must have the same height. Then we overlap them. For this example, I used an overlap of 100 pixels. This is the overlap we are interested in. Now we calculate the error for this overlap. It's much easier to remove the color at this point. Then we can perform the subtraction and square it to get only positive values. Here's what the error section looks like. Inside this error section, we can calculate the path with the minimum cost. Visually, that would be the darkest path. This is the path where all overlapping pixels look alike the most among all possible paths in the error section. This path can have any shape, but for our example, it's strictly vertical or diagonal, never horizontal. Lastly, we use pixels from the left picture at the left of the seam and pixels from the right picture at the right of the seam to create the final image. And there you have it, a Bengal tiger in my neighborhood. Let's look at an example where we remove a piece of litter by splitting an image in two parts and then stitching them back together with a cut that excludes the unwanted piece of litter. For this, we'll work with the picture of a green wall. This would be a nice photograph to share if it weren't for that pesky piece of litter. Now let's split the image in two separate parts, right at the piece of litter. Notice in lines 3 and 4 that I'm making the split at column 870. Notice the piece of litter in both images. Alternatively, I could have split the picture a little to the left and right to completely exclude the unwanted object. However, I decided to leave it there and use a large enough overlap for my algorithm to have enough opportunity to take it out. Now let's look at the two images put together in a vertical straight line at the middle of their overlap. In line 4, I've defined an overlap of 70 pixels. After watching this video, try using other overlaps, like 52 and 46. The vertical stitch is done in line 8. Don't worry, I don't expect you to notice the split artifact in the middle because of the resolution. So let's take a closer look at a sub-image named Tiny Stitch. There it is. Can you spot the vertical artifact in the middle? Now I want to show you how the cut will be created at a good level of detail. So I'll calculate a cut for a small section of the overlap. This will be a 100 pixel tall section at the top of the overlap created in lines 6 and 7. Remember, these two parts will overlap. In the next cell, I'm producing the squared error of the overlap in 3 steps. First, I remove color, then I subtract, and then I square. Now here's where we calculate the cut. It must be the darkest path of all. That is, the path that accumulates the least possible sum. So to do this, I'll use a function I wrote called getSeam. Let's go to ECCV. The function is defined in 993, and it takes a square difference matrix as an argument. Now the algorithm is a bit involved, and you are not required to go through the code. However, if you really want to know, this is a graph search algorithm like A* or Dijkstra's algorithm. Simply put, in the first set of nested loops, I traverse the error matrix top-down, row by row, adding the values of the shortest sums into another matrix named cost. In the second set of nested loops, I populate an array named seam by traversing the cost matrix bottom-up, selecting the pixel index with the minimum cost. Once again, don't worry too much about this code. Let's go back to the notebook. Notice that I'm calling the getSeam function in line 5. Then, in lines 8 through 11, I'm simply marking the seam in the error image with white pixels. Let's see it. This is the darkest path in the error image. All other possible paths add up to a bigger cost. Great! Now that we know what we're doing, let's create the whole seam. Basically, I'll repeat the steps we just saw, but for the whole overlap. Here we have the 2 overlapping sections. Now let's see the squared error image. This is what we'll send to the getSeam function. Remember, in this cell, we'll calculate the seam and show it in white over the error image. This is the complete cut. Let me scroll down. Now comes the easy part, stitching the sections together. In line 6, I'm creating the middle section, which has pixels from both the left and right components of the overlap. The seam determines where the left pixels end and the right pixels start. In line 17, I'm creating another version of this middle section, which will be marked with the seam in red pixels. Let's see it. Here it is. Let me scroll down. Now in this cell, I'm stitching it all together. The leftmost image minus the overlap, the middle section with the seam in red, and the rightmost section minus the overlap. Admittedly, the red seam is barely visible. Now let's see the result with a middle section that doesn't have the red pixels at the seam. This is the finished image. Once again, at this size, it would be difficult to spot any artifacts, but it's looking good. Lastly, let's zoom in to see the difference in the magnified section we saw before. At the left, we'll see the vertical split, and at the right, our nice cut. I'm sure you can notice the vertical split, but I dare you to try and find any unnatural artifacts in the cut version. Also, look closely to notice how each artifact in the split image was corrected by the cut. Feel free to pause the video to examine these details. Let's save the resulting image in a file. You can go ahead and open it to see it at its full size. Here you can try harder to find any artifacts. Now let's have some fun. In this cell, I repeated the whole process, but I inverted the right and left sections to see how the cut ends up. Let's see it. Well, that doesn't look bad at all. Notice the piece of litter still at the right and left ends. That can be easily cropped away. Now let's see the usual zoom. This time the vertical artifact is very visible, and the cut did a wonderful job. Lastly, let's look at the grass. As you can see, the quality of the cut is impeccable. Now I want to tell you about the application of cuts in panoramic photography. You're probably familiar with panoramic photographs, and if not, chances are your smartphone has this feature. A panoramic picture is the result of taking several pictures, like the 3 pictures you see here, and producing a combined picture as if it were one single wide photograph. Now, the software behind panoramas consists of a specific pipeline of processes to adjust the separate pictures. For example, if you look at these 3 pictures, you'll see that the electrical cables at the top don't match between the pictures, nor do the angles of the fence. That's why the algorithm includes a step of warping the pictures to make overlapping elements match. Here we can see the 3 pictures stitched together with 2 important details. First, the pictures are warped in such a way that the electrical cables and the house overlap quite well at the right. And so do the fence and the lamppost at the left. There are several algorithms to warp images depending on the effect you want to achieve in your panorama picture. Second, the original pictures had overlaps shown here between vertical green lines. Those overlaps were combined with a technique called blending. This is a weighted sum of the overlapping parts so that one fades away while the other fades in. We can see that blending was used in this picture because of the ghosting effect at the seam between the 2 rightmost images. The final step is to crop the image to remove the visible excess of black at the right, due to the rightmost picture not being warped at all. The final picture looks very much as if it had been one single wide photograph all along. Blending is usually very good to stitch 2 pieces of panorama pictures, but so is cutting. Let me show you an example where I stitched 2 parts of a panorama together, first with blending, and then with a cut. Notice that I blended the images at a different horizontal point than where my algorithm ended up making the cut. Now let me zoom in to take a better look at that cut. Here we have the cut, which was calculated with the same algorithm we just saw. Notice that if the warping stage is good enough, the cutting stage will usually do a good job because of all the similar overlapping pixels. Now here we have the same image without highlighting the cut. Go ahead and try to find an artifact created by the cut. The only one I can spot is the discontinuity in one half of the roof. The rest looks tidy, especially the sky. It's time for another challenge. This time you'll stitch two pictures together. In task 1, you must choose a pair of pictures to stitch together and display them. These two images must have the same height and must be suitable for stitching together. They may be two parts of the same picture, or they may be two different pictures with similar shades and tones. Task 2 is to find a suitable overlap for these two pictures. This overlap can be a number as small as 10 pixels or as large as 100 pixels. It all depends on your picture's resolution. Then you must produce an appropriate seam and display it. You may do this in several cells. For task 3, you have to stitch the images together. You may use 3 sections like I did. Finally, don't forget to display the resulting image. This should take you about 30 minutes. I'll show you my solution in the next video as usual. How did you do? For my solution, let me give you a peek behind the scenes into the production of the video where I explained the stitching of the pictures with purple flowers and a tiger. This is the code I used to produce those images. For task 1, I used the files left.bmp and right.bmp. These are the purple flowers and the tiger. For task 2, I simply copied the steps to produce the seam. Notice in line 15 that I chose an overlap of 100. The rest of the code finds the seam and marks it in white pixels. Here it is. Let me stop here. The fact that a seam lingers at one end, right or left, shows that the algorithm had no choice and was cornered. So that part of the seam may not be very good. Notice that the flowers are getting in the way. Alright, let's move on. And for task 3, we have the code for putting it all together. And here we have it. The worst part of the seam, where the rightmost flowers are, doesn't look so bad to me. For the last application example of image processing, let's look at a series of operations called morphological transformations. These are widely used in computer vision, which is the application of computing to make sense of images and video. For example, software that recognizes handwritten text, faces, or people. Morphological transformations are typically used in black and white images with blobs, which are polygons that represent objects in a picture. These operations change the shape of blobs. So with these operations, we can make blobs shrink and grow. To show you why we need to modify objects, let's look at a computer vision process. Suppose we have a robot that moves boxes in this warehouse. This robot must go from its starting position to a finished position where the target box is located. This is a messy warehouse, so the robot must be capable of moving around without bumping into boxes that may be lying on the floor. Looking at the size of the robot, the only path to get past the boxes at the left is through the middle, like this. Now, despite facing a narrow path, the robot can certainly fit through it. And finally, it can reach the finish point. So, how can this robot come up with this path before starting to move? Well, this is a special robot with a wireless connection to a camera fixed to the ceiling looking straight down. That camera took this picture and sent it to the robot when it was at the starting point. With this picture and the start and finish points, the robot, or some other computer, can process this image and try to come up with a feasible plan of action. Let's look at a simple image processing algorithm to help this robot find its way. The first step is to create a black and white image with a set of blobs where the obstacles are. This is known as a color mask. Notice that the obstacles produced white blobs. Now this step isn't perfect, and it's not expected to be perfect, since not all boxes will look the same, and the lighting won't always be the same. An artifact that's getting in the way are the many white dots scattered all around, but especially the ones in the path we know the robot must follow. For this reason, the next step is to get rid of these small dots. We can do this by shrinking every blob a little bit. Just enough to make these spots disappear, but not the large obstacles. This operation is known as erosion, and it means reducing the size of white blobs. As I erode the mask, pay attention to the size of the larger objects and how the tiny spots disappear. Notice that only one artifact at the bottom left survived the erosion. Now we have two problems. First, we just eroded everything, so the obstacles are a little smaller. Second, remember the size of the robot. Path planning algorithms usually don't keep track of the robot dimensions. Instead, they consider the robot to be at a single point, like a particle. This is a problem because the resulting path may go too close to an obstacle, finally making the robot run over it. A usual solution is to make all obstacles grow about the radius of the robot, so that the calculated path is guaranteed to avoid obstacles completely. So that's why in the next step we perform the opposite of erosion, which is dilation. Next, I'll dilate the mask many times so that obstacles grow enough to produce a safe path. Look closely. After dilating the mask, we have a clean image representing the grown obstacles in white and the floor in black. To find a path from start to finish, we simply feed this mask to a path planning function that implements an algorithm like A* or Dijkstra's. The function also needs the start and finish points, and it will produce the path we need. Now don't worry about the narrow parts of this path or the near misses with the obstacles. Let's see how this path looks in the actual picture. As you can see, there's enough room for the robot to take the path safely. Erosion and dilation make white blobs shrink and grow respectively. Now, the usual algorithm for this is similar to the median filter. For erosion, a pixel is turned black if there are black pixels in its neighborhood area. For dilation, a pixel is turned white if there are white pixels in its neighborhood area. Let's get to know OpenCV's erode and dilate functions. First, let's open a black and white picture with some text in it. This image has white text over a black background. This is the usual case in computer vision. In line 3, I've defined a 3x3 kernel of all ones, which I'm using in the erode function in line 5. This function takes as arguments the image, the kernel, and the number of erosions to perform repeatedly. Also notice in line 7 that I'm saving this picture for later in IMG3. Let's see the result of one 3x3 erosion. The text at the top lost a lot of vital pixels, while the text at the bottom is still readable. Notice that the term erosion refers to white blobs being eroded or diminished in size. Now let's dilate this once with a 5x5 kernel. As you can see in line 4, the dilate function works with the same logic as erode. The lost pixels in the text at the top really damaged the shape. Now the text at the bottom looks better. However, look at the letter R. These are not aesthetic operations. Now let's see what happens if we erode this image back with a 5x5 kernel. It looks like we got back to the same state before dilating, right? Wrong. Let's compare this image with the one I saved some steps back. At the left, we have the eroded image, and at the right, we have the result of dilating it and eroding it back with a 5x5 kernel. As you can see, these are not the same image, so dilation and erosion are not exactly inverse operations. Now let's see a different picture of a few figures. Let's erode those shapes 4 times with a 3x3 kernel. Once again, notice that the shapes were not exactly preserved. The vertices in the triangle got pointier and the star was deformed. Now let me dilate the image twice with a 5x5 kernel. Notice that only the square maintained its shape. Now let's repeat the same experiment we saw before, but this time let's erode first and dilate later. In line 3, I'm saving the initial state. Let's see an extreme erosion with the 5x5 kernel, and let's do it 8 times. Look, the arrow disappeared altogether. Now let's try and get it back to the larger state. So let's dilate 8 times with the same kernel. Let's see the result side by side with the version before eroding. There you have it. Only the square seems to have gone back to its original size. Also, we may argue that by eroding and then dilating, we got rid of the arrow. Sure, the shapes are deformed, but the arrow is certainly missing. Open and close are special operations intended to get rid of small imperfections by performing erosions and dilations. Open erodes first and then dilates. Close dilates first and then erodes. Let's start with a picture that contains shapes and imperfections. Now let me show you a close-up of 2 special shapes in there. I'm talking about those tiny swirl-like shapes, one inside a blob and one in the background. Let's see what happens after an open operation with a 3x3 kernel. Remember, open means an erosion followed by a dilation. Let's see the original image and the result side by side. The swirl inside the circular blob got solid, as if we opened a hole on the shape. All tiny spots in the background disappeared, and all black spots in the shapes survived. Now let's see if we can get rid of the black spots in the shapes with a 3x3 close. Yes, most of them are gone. Only the larger ones survived. Now let's work with the 5x5 kernel. Let me open once to get rid of the tiny blobs. Now let me close to close the holes. Now let me zoom in to show you what happened to the swirl-like shapes. So this is the result of opening first and then closing. Notice that only the swirl-like shape inside the circle survived. Now let me show you what happens if we close first and then open. Now the swirl-like shape in the background survived. So now we know that when it comes to open and close operations, the order matters. Are you ready for your last challenge? Don't worry, this one is easy. In this challenge, you'll help the warehouse robot we saw earlier find its way to the box of interest. You'll have to run some cells before getting to your tasks. First, here we have the picture taken by the camera in the ceiling as requested by the robot. In the next cell, I'm performing a procedure to identify the blobs coming from the boxes. This procedure is described in OpenCV's tutorials website. The URL is in the comment if you'd like to see it. As you can see in the code, this procedure involves working with the HSV representation of the image to produce a mask. That mask is the black and white image with the blobs. This one. Notice that it has a lot of lingering white spots that are not actual obstacles for the robot. In the next cell, we have a close-up of the narrow path we know the robot must cross in the end. Notice the noise dots scattered all over. Also notice that the rightmost box appears as 3 separate blobs because the packing tape wasn't detected as an obstacle. We definitely don't want a robot to try to go through that box. And this is where you come in. Task 1 is to get rid of the noise. In this cell, use morphological transformations to get rid of the white dots throughout the mask. After that, task 2 is to make the blobs grow. We want to do this for 2 reasons. First, we want to account for the size of the robot, as I explained earlier. And second, remember the box with the packing tape gap? Well, we need those segments to become one single obstacle. This task is very simple. Just dilate the mask with a 5x5 kernel about 10 times, or with a 3x3 kernel about 20 times. Lastly, run all cells again, but skip task number 1 to see what happens. This should take you about 15 minutes. When you are done, watch the next video to see my results. Let me show you my solution. Here's the mask with the white dots. Now, for task 1, I simply eroded the mask once with a tiny 3x3 kernel. You can see the code starting at line 8. Let's see it. As you can see, all the noise is gone. Now, some of the shelves in the upper part of the picture are almost gone. Now for task 2, I followed my own advice and dilated the mask 10 times with a 5x5 kernel. Here's my result. There you go. As long as there's a black path from the left portion to the right portion of the warehouse, this result is useful to the robot. Now let me repeat the experiment, this time skipping task number 1. That means leaving the tiny white dots before dilating. So first, let me restart the Jupyter kernel and clear outputs. Now let's run some cells. And let me skip task number 1. Notice what happens when I run task number 2. What a mess! Now the robot can't find a path because of all the magnified noise.